Okay, so hi guys. So in the abstract presentation, we already discussed, we give an overview of what is Anova. So today in this discussion, we'll get in depth into the theory of Anova and the types of Anova and what does it actually solve, what is the need for it, right? So let's consider the situation. We guys start working in a company and we are being given a problem to develop a model, a classification model. Let's say the most common problem that we have discussed here is house price prediction, right, in this class. So let's take that. So we build a simple, let's say, linear regression, and then the data is some n number of rows, each row corresponding to a particular house and its details, and one target column as to what is the price of the house. Understood? This is the data set. Now, given this data set, we have a linear regression model, and we trained the model. We got the results. Let's say the model is performing at an accuracy of 95%. Now, I have this trained model. Now it's the moment of truth. I want to test the model. I want to pass data to this model that the model has previously not seen. It's the test data. Now, the model is giving me an accuracy of 40%. We need to find the reason for this. We can't say that the model is really performing well on train, so we can ship this model away. You can put it to production. We can't say that because the model is not performing really well on the test data, right? So how do we debug this? How do we know that the error is where the error is? How do we know where the error is coming from? Is it from the data, underlying data, or is it from the model, the code that we have written? So where is it? So let's assume that the error is from the model. So from linear regression, which is the basic, basic linear model that we can use, to let's go to a completely non-linear model, let's say neural network. So we employed every model available, and still the results are same. 90% on the trained data and 40% on the test data. Now everything falls back to the data, right? So we have tried everything with the modeling part, nothing changed. So the only thing that we can play around with is the data. Now we have this trained data, the n number of rows that we use for the training, and we have this test data. So something in this data is changing. That is why we are not able to get the results. Now, how do we analyze that? One technique is, so in the training data, what do we have? We have the house ID, which we won't use for training, and let's say we have the number of rooms, number of bathrooms, square feet, and the location in the training data as columns. Now, if I start comparing the train data columns, so I'll just train data, test data. 1, 2, 3, 4, 5. So this is column 1, 2, 3, 4 and target. 1, 2, 3, 4 and target. Now let's say this is my number of bedrooms. This is square feet. This is location. Okay. So what do? Again, this is a number of bedrooms, square feet, location.
I think location cannot be put in that set. I think the location gives you another nature. I don't know whether, for example, location can be converted to some numbers. So if you say, okay, number of bedrooms, it's number, square feet in the number.
Yeah. So this location is a categorical value, which is a string. So we need to encode that, and
itself is a classification, right?
Yes.
So when you say location, you can do classification based on location.
Right.
So
So I did not mention that for the simplicity's sake. So let's consider that we have encoded it to a numerical value.
Okay.
So we encoded it to a continuous numerical value by taking some sort of a frequency.
Allocating value to location.
Yeah. So we did some numerical representation of this column.
Okay.
Now, the basic thing that we can do is we need to compare these two data sets. Mm-hmm. How can we compare? Let's take column 1 with column 1. Has anything changed? So basically what we do is mean and standard deviation comparisons of two columns. We take this, do the comparison. We take this and do the comparison. In our comparisons, what we found out was this column and this column is totally different. Now looking at, now we know that the column is different, right? From these two data sets, this column and this column is different. Now if we go to my raw data, this data is coming from California and this data is coming from, let's say, Worcester. That means we can't compare these two, right? Because the model has not seen data that is coming from Worcester. It's just seen data coming from California. Then I can't use that model for Worcester, correct? Now I got that. Now I got the issue. The issue is this. But let's say in a real world scenario, we won't have 3 or 4 columns, right? We'll have thousands of columns together. We can't do this one-to-one comparison. We need some sort of an analysis tool to tell us that data from training and data from testing is, what is the relationship between these two? Are they completely different, different in their respective scenarios, or are they same? So this kind of comparison can be extracted using Anova, which is analysis of variance. So the name is, analysis of variance has got nothing to do with each column's variance. What we are doing here is taking each column, playing with their means, with their individual means, and comparing them. That's what we are doing in analysis of variance. So I think you now have the idea of why we need Anova, right?
So is it like column by column then, or in general could be the whole matrix by whole matrix?
So professor, in p-test or t-test or the example that I showed you now, it's column by column. In Anova, we can take the complete matrix and compare. So we can take the whole thing as a matrix, and come up with a statistic that tells us whether these two matrices are same or different. Now we will see how we're gonna do. So after knowing the need for Anova, so let's discuss the agenda. So I spoke about the motivation, the need, and we'll talk about the history and the contributions, who was responsible for this algorithm, and we'll see the applications and the theory behind that, and types of Anova, and we'll summarize the presentation. So yeah, motivation is this, the same thing. It's one of these comparison tests I spoke about is called t-tests. There are again variety of t-tests which take the whole matrix and compare, but it has its own flaws. We'll discuss that too. So because these tests fail in giving us a good metric to do this comparison, we fall back to Anova. Now history. A person called Ronald Fisher in 1918 actually came up with this algorithm, but put this algorithm in a book in 1925. And since then it's been pretty much used in a variety of industries. The reason this became very popular was back in that times computation was very hard, and this is a matrix computation, and for matrix computation we need a huge computational power, right? But this algorithm, even though if it is a matrix computation, it doesn't require that level of matrix multiplication. That complexity is not required. Why it's not required, we'll figure out. We'll talk about it. Okay, again, what can Anova do is t-tests fail because of the same reason I showed, and Anova can do comparison of more than 2 populations. So population is, this is population 1, this is population 2, 3, 1, 2, 3. So you can do multiple population comparisons, and also, as professor said, this is a categorical variable, right? So this can be California, this part can be California, this part can be Worcester, and this part can be the whole of Massachusetts. Let's say this is some other state. So this is subgroups, right? Within the same group, it's a subgroup. We can also do the comparison within these subgroups. So my friend will discuss about how these things happen. So this is what Anova can do on a higher level, on an abstract level. I hope this is clear. We'll move forward. Any questions?
Just here, let me add something. Very good presentation so far. What I want to add here, the t-test. I don't know, you are...
We are going to explain hypothesis testing.
Okay, good.
So some of the applications of Anova, before actually diving into the theory and how we calculate that statistic, we just talk about the applications, where it's used. So in manufacturing, to choose the least expensive metal given a set of metrics, they use this. And in enterprise, to effectively determine possible errors in a particular manufacturing unit they use this, and to do the food quality control in healthcare. So after we discuss the theory and how things are rolling out, these things make sense to you, where and how it can be used. Now my friend Pratyush will talk about the theory and how we actually come up with the statistic.
So coming to the concepts, before that, I guess my friend forgot to introduce us. I'm Pratyush and he is Srisha, for those of you who don't know. So what is hypothesis testing? So analyze tests an assumption regarding a population parameter. So let me give you a background of hypothesis testing. Let's say you are given a data set and it has 3 columns, and let's say the same example, the number of bedrooms and which area it is and the square feet, and whatever the target variable is, the price. It's a regression problem. So what is my intuition? My intuition is when I go through the number of bedrooms and the square feet of area that is covering, I can see that when it is increasing, the price is also increasing. So they are directly proportional to each other. I can get this intuition using, so this intuition is called as hypothesis. Now, you need some proof to actually show that your intuition is right. It may be right, it may be wrong, because your intuition is on a sample set of data. It's not on the entire data. You can't observe a million rows and think. You'll always sample. You'll sample thousands of rows and you will see this is the thing. So for an example, let's take a coin. A coin has 50% chance of turning heads. So this is a phase statement. Do you guys agree that this is a phase statement?
For a fair coin.
Yes. So that is the hypothesis. When you have this hypothesis, you should be able to provide some proof, concrete evidence that only if it's a fair coin, this is true. If it's not, it falls. So like this is the hypothesis that you will have, and this is a way of testing. So then there are a lot of ways to test this hypothesis. The most basic way of testing is null hypothesis. What null hypothesis says? It says that nothing new is happening, and there are no association among groups. There is no relationship between two measured phenomena. So what this all usually mean is the relationship is due to sampling method. Let's say you have 2 columns and you are sampling them. The relationship between those 2 columns are random in nature. It's not because the relationship actually exists. It's because we have picked in such a way that that relationship exists. So that's what the null hypothesis states. So for example, null hypothesis for this is 0.5 for a fair coin. So then we have one more important concept that is called as confidence interval. It says that the range of values we are fairly sure that our true value lies in. So what does it mean? Let me give an example. So we measure, let's take an army of soldiers. Among them, we measure 40 randomly chosen men. And this is the mean height. Among the 40, we have 175 centimeters as the mean height. And the standard deviation is 20. Now, can we state that the mean value of the entire population is 175? So then comes a concept called as confidence interval. So if I ask you the question, like if the mean value is 175 that is calculated, how confident are you in that mean? So that's what the confidence represents. And the interval, what it represents is among the 40 randomly chosen candidates, if I actually do this experiment 100 times, like let's say there are 1,000 soldiers, I'll take first 40 and I'll get the mean of it. Then I'll go to the next, then I'll go to the next. Likewise, I do hundreds of experiments. Among 100, in 95%, we are getting a mean between these two ranges. It is between 168.8 and 181.2. So this is my margin of error. So this is the confidence interval. The 95% of the time, in my 100 experiments, the mean is 175 centimeters with this margin of error. So this says the true mean of all men is likely to be between 168 and 181. So this statement is actually false. That is because only 95% of the experiments we saw, this is the confidence interval. The remaining 5%, it will be different. So there is 1 in 20 chance. So that this 20 is nothing but the standard deviation. is what in the problem that I stated. So there is 5% chance that our confidence interval does not include true mean. So are you guys clear with confidence interval? Okay. Now coming to the next concept, we need to understand what is F ratio. So this ratio determines whether or not there are difference between two groups. So let me give you an example. So let's take a food manufacturing company. So there are two machines, let's say M1 and M2, and it's producing 100 cans of 100 grams of noodles every day. Okay. Now let's assume that you are a QA engineer and your job is to analyze how these machines are performing, and if there are any errors, you have to calibrate the machines. So how would you do it? This is the data that we get. We have machine M1, we have machine M2, then the samples. Let's from 100 cans, we are taking a samples. So this is what in a batch we pick samples and we test. And this is the mean weight. You can see there is a small error. It's an increased weight, 100.052. Then this is the variance among those samples, and this is standard deviation. The same thing for M2. Now, can you guys tell me what are the errors that you can look at from here? So one common error that we can see is there is a change in variance, right? So there is actually one more error. So there is sampling error. So the change in variance means the machine is not performing well. The machine is not placing the packets properly, or it's placing more in the first M1 and less in the M2. But before concluding the machines are wrong, we need to see whether our samples are properly selected or not, because there is a change in samples. In M1 we have taken 25 samples, in M2 we have taken 22 samples. Whether our sampling method is proper or the amount of samples is corrected is proper. So that is the difference that Anova gives. Using Anova, you can decide whether this is a sampling error or is it a machine error. So any questions regarding F ratio? So how do we calculate F ratio is, we take the largest mean, so this is the largest variance, and we divide it with the smallest variance. So we'll get a number. And this is the distribution plot. If we plot the distribution of the packets, we'll get a plot like this. And this is the 95% confidence region. So if our ratio, the F ratio belongs to this region, then that means both of the machines are working properly. The error was due to the sampling, how the method of sampling used or the number of samples that are taken. But in this, our F ratio is 8.2, so that is far outside our non-rejection region. So this means there is actually difference in those machines. Those machines are not working properly. It's not an error because of sampling. So reject hypothesis. Now coming to t-test. What t-test does is it is used to determine if there is significant difference between the means of groups. Are there any difference between two groups? And it gives the probability of difference. So how do we calculate t-test? It needs difference of mean, there is standard deviation, and there is number of data values. So we are not going to explain in depth how t-test is going to be calculated, but what we'll tell here is what it's needed to calculate t-test and what the result it will give. It gives whether it's significant difference between the means of two groups. Now let's come to Anova. Since we have understood the basic concepts. So in this example, we have three random distributions. So we just have three populations, x1, x2, and x3 are the mean of those populations. Now what can we infer from this, from these three populations? So the first thing comes to mind is, are they from common population? Like, are they same? The background behind these populations, is it a common distribution? Or are each of them are from different populations? So this is the two questions that comes up. So how do we answer this is, we'll take these populations and then we draw a global distribution. Like take all the data points in the data set and then plot a global distribution. Now we can see that these three populations, population means, lie inside a global distribution. That means these samples are not from different data set, they are from same data set. So this is one case. The next case, one of the mean is outside our global distribution. So this means x3 is not from our data set, x3 is unique in nature, and x1 and x2 are from the same data set. Now, coming to null hypothesis in Anova, what does it suggest? It suggests that the mean x1, x2 and x3 are always same. That means it doesn't mean that it's exact value, like it is not 20, 20, 20. What it means is all of them are lying in the same distribution. That is the null hypothesis. So that is case A. The case B is the rejection of null hypothesis. That means each of them have their own distribution. So this is the case B. Now, we understood like using t-test we can compare two populations. But now the reason is why Anova? Why can't we use just t-test and compare all these populations? So let's take on my left hand side it is x1, x2, x3, there are three populations, and on the top there are three populations. I'll be comparing x1 with x2 and x3 with x2 and x1 with x3. So with a confidence interval of 0.05, that means 95% confidence interval, the alpha. Using pairwise comparison, all three tests with alpha of 0.5, the type 1 error rate at 95% confidence. So this is what we are calculating. So let's say we get some values. We'll know what is the relationship between x1 and x2, x1 and x3. Let's say we got some values. But those values are only 95% correct. The probability is just 95% confidence that we have calculated. But to know the entire probability of the test, we have to multiply them. So we know that it's 95% confident for x1 and x2, then x1 and x3, then x3 and x2. If we multiply that, we are only confident at 85%. Our confidence level dropped from 95% to 85%. So that's an increase in 14.3% of error. So this is the main reason why we can't use, let's say there are hundreds of variables. So this keeps dropping. Even though we calculate t-test, our confidence in them drops. Using Anova, we can solve this. So let's take Anova. There are two variations. The type 1 variation is if we plot three distributions and their global distribution. So this is the mean of the global distribution, and these are the mean of the sample distributions. Now what is the distance between this mean and the global mean? So this is the variation, first variation. The difference between x2 and global mean, x1 is right at the center and x3 and global mean. This is the first difference. And the next difference is among, like in this, it is around. Within the means, what is the difference? In the first we thought, what is the difference between the global mean and each of the means? Now we are thinking how will the spread in each distribution. So these are the two things that we need to understand. Am I clear on these two? Now, to calculate Anova, what we have to do is, we have to divide variability among or between means. That means from central mean, how much it is varying, and then variability around means, like what is the spread of each population. If we sum these differences, remember it's not summing x1, x2 and x3, we have to sum up this difference. We are summing up those differences in the numerator and again these differences in the denominator. Using this, we'll get a ratio. So if the ratio is 1, that means all these distributions are unique in nature. If the ratio is less than 1, then they are in the same distribution. Now let's understand the ratio. If the numerator is large and the denominator is small, so we have to reject the null hypothesis. What does it suggest? At least one mean is an outlier. One of the population mean is outlier. Each distribution is narrow and each distribution is distinct from each other. This is what we learned. And if both are small, the numerator and denominators are small, that means they are fairly close. Distributions overlap a bit and it's hard to distinguish. But if numerator is small and denominator is large, the distributions melt together. They are totally the same, almost the same. So now, Srisha, any questions regarding these slides?
Oh, how are we running on time? We'll take another 5 minutes. I'll quickly run you through the application of Anova. So here we are going to discuss only one way Anova today. So we'll just tell you the intuition behind 2 and Anova. So the one way Anova, right? So just to summarize on what he said, we use F statistic, the F ratio he spoke about, to say whether two data sets are, two populations are similar or not. Okay, irrespective of p-test, me-test or Anova, we use these statistics. Now, how does this statistics in Anova extracted? How is it extracted in Anova? That's the question. Using one-way Anova, we do that. Now, I have a data set, column 1, column 2, column 3, or it can be two columns of any other data sets, or it can be multiple columns. Basically, for the demonstration purposes, I just took 3 columns. Now, what I do is, for each of this column, I calculate its mean. Okay, and take all the columns and calculate one mean. So this is the overall mean, and this is the column mean. Now, what I do is, I need few things here. First is sum of columns, squared sum of columns. So to calculate squared sum of columns, what I need the column mean, and then the deviation squared, right? 82 minus 71.1, the whole square. I do the same thing and add it up. Okay, so that's what I'm doing here. This is the deviation of the error from the within the column. Now I need the error in between the column and the overall mean. So I take the column's mean and the overall mean and find the deviation and square it, and then sum it. So I got two things here. I got the first thing, I got the second thing. That is, within the column I got the error, and between the column I got the error. So the within and between, my friend explained, that's what this is happening. That's what this does. Now what I do is, I put up this formula, that is SSE, sum of squares within the columns, this one. I calculated this. Sum of errors, that is within, I calculated this. Now I need to calculate the total error. What is the error across and within, both? For that I need some few things. First I need to calculate the mean of my sum that I calculated within the columns. So that I do by the sum divided by the number of columns there is. Here I have 3 columns. Since it's a sample variance, I calculate n minus 1, and then this is sum of squares. So I already calculated the sum of squares, and for that I do the same thing. I calculate the mean. So mean is the number of columns, the number of observations minus the number of columns. So using that I calculate the mean. Now F statistic, the actual value that we use to compare, that's calculated by mean of the column distribution and mean of the error distribution. This gives me a value that I can say, looking at the value, whether the columns that I considered in the initial phase, these columns, do they come from the same population or not? All of them have some common thing in them or not? Or are they totally different? Now, so don't look at any of this, we just talk about this. So I got this score by dividing the among and within means. I got this score. Now, as my friend said, with a confidence interval of 95%, that means I am okay with a 0.5% error, 5% error, and a total of 20 values. If you go back and look at my slide data set, it has 20 values. Okay, with the 20 values, there is a log table. So I think most of us are familiar with log table. Similarly, we have a F statistic table. I think the professor can add more on this. There's a F statistic table. It says, given a particular confidence interval and given the degrees of freedom, that is the number of samples we have, I am okay to have this much of a score. That means if my F score is within this much, then the data sets I'm comparing are equal. So it's a standard, log table kind of a statistic. So if we use this and find the value, this is what we get, 3.55. If my statistic, if the value that I found out is within this value, then my data sets are equal. And here it is, right? So I'm telling that the data sets I'm comparing are equal. So going back to our actual use case, if I crunch these columns together and find out this F value, and if the F value is within this range, then I can say that these two data sets are same. But in the case that we discussed, this f value is going to be very high because these two data sets intuitively itself are they different. We don't need a statistic for that. Intuitively they're different. So this is how one-way ANOVA calculates the f statistic. So here we are calculating f statistic keeping in mind all of these values, all of these columns. So we are having multiple distributions here, and still we are getting the f statistic with a 95% confidence interval. But when my friend demonstrated the t-tests confidence interval for multiple columns, it started reducing, right? So that's one-way ANOVA. So two-way ANOVA works on subgroup level. Two-way ANOVA also considers a subgroups level and then gives us a confidence interval. And MANOVA, so for example, in data science, usually what happens is there are 3 columns, and taking these 3 columns, we can create more columns. We can derive multiple columns based on these 3 columns. So these are not raw columns that we derive. They are not coming from actually the data. We are just doing some mathematical computation and creating these extra columns. So in that case, these columns also can be considered using MANOVA to get the distribution relationship. So yeah, that's what it is. So MANOVA helps us to get the F statistic, F score of 2 data sets, 2 distributions, and lets us compare multiple columns of them with a 95% confidence interval, which is not possible in basic t-tests or or any mean comparison algorithms.
Okay. So coming to the summary, we learned the motivation behind ANOVA, why ANOVA is required. Then we learned the history. Then the reasons for population comparison, why Srisha gave an example. Then the issues associated with t-tests. Then we discussed few of the concepts that are required for ANOVA, that is hypothesis testing, null testing, then confidence interval. Also we discussed t-tests. And finally how ANOVA is calculated, the theory, and one-way ANOVA. So if you have any doubts, like, we can answer.
Okay, very good, very good. I think that you covered hypothesis test, t-test, etc. So I'm not going to teach them again. So we are done with teaching. And the only person that wanted to learn this, she didn't attend your presentation. So, but anyway, now I'm going to cover that. But this area actually is huge, okay? So, and as you continue talking, there are lots of things to talk. I mean, it's never ending. This area is big. I mean, when you get to the hypothesis test, it's basically the different tests like z-test, t-test, p-value, etc. And there are all different variations of them. I mean, it's kind of like, if you want to get into that, it has its own world. We are basically trying here. What you did, it was good. You tried to open a window to this world. And what we are going to cover in the class also is going to be just a summary that we try just to open the window to this world to you. And if you get into that, I mean, there are a lot of things to dig into. So it's a huge area. There are different variations. And, very good, a new presentation. And you did great. I think so far, among everybody, you are within top 2 so far. Okay.